The next topic I'm going to talk about is using graphs to solve equations. So when you have a graph, when you solve an equation, you're looking for the points where the graph crosses the x-axis, okay? Because the x-axis is actually when y equals 0. This is why we put quadratics equal to 0. We're actually finding where they cross this axis, okay? And remember, your calculator can solve this for you and give you those coordinates, but we'll factorize this and we'll get x minus 2 and x plus 1. So when I put that equal to 0, like I do for solving these, I get x equals negative 1 and x equals 2. So we've got negative 1 here, we've got 2 here, and what we then have to do is, it will say, well, what's the solution of a graph that looks very similar to this, x squared minus x but minus 3? How am I going to find the solutions from that, just from this graph, without using my calculator? Although we will do that to check our answers at the end. So if I call this function f of x, then this one here is f of x minus 1, because the difference between this one and our new one is that it's just had a minus 1 there, okay? And you know from your graph transformations, which I'll talk about more in detail, but f of x minus 1 is a shift down of the graph. So I could either redraw this equation again as shifted down by 1 and find in the new coordinates where it crosses, or I could draw the line y equals 1 and see where that new line, y equals plus 1, I can see the new intersections here and read those off on my graph. Okay, so where the new line intersects with the old curve, that is the solution for this. But I could just put this into my calculator and get the actual values and then double check where these x coordinates are, and that will help me to determine if I've got this answer correct. Okay, but if we start with our new equation here and I rewrite the old equation on top, x squared minus x minus 2, okay, then what we've got here is we've got a difference. When I go from this one to this one here, I've got a change of minus 1, so I'm going to change this one here to minus 1 as well. I'm going to subtract 1 from this side and I'm subtracting 1 from the other side. So what I have on the left is y minus 1 equals 0 when I subtract these. Okay, subtract this, subtract this, subtract this, and I can then rearrange this to get y equals 1. So that tells me the equation I have to draw on here to get this solution. Okay, we look at the next one. We have y equals x squared minus x and minus 2. When I look at these two equations now, I have to plus 1 to go from minus 2 to minus 1, so I'm going to do plus 1 here. And to go from minus x to minus 2x, I've got to minus an x, so I'm going to minus an x from this side. And so I have on the left, I have y minus x plus 1 equals 0. So I rearrange that to get y equals x minus 1. So that means now that I have my equation of y equals x minus 1, I would plot y equals x minus 1 on my graph, so it goes something like that, and I would read off my new intersection points here and here, and that will give me the new solutions of my graph. But before I draw that, I would actually put this into my calculator. Okay, y equals x squared, 1x squared, negative 2x, and negative 1, and I get 2.41 and minus 0.41. Okay, so I know that this one here is minus 0.41 and my other one was 2.41 like that. So I'm using my calculator to actually solve this in the normal fashion and then making sure that my line goes through these points to give me my accurate solutions to these graphs. With vectors, what we have to do in the first parts of the question is usually relatively straightforward. Go from one point to another point using vectors. So let's say L to M is A and L to O is C. Okay, so we put these on here, A and C. And if we want to go from one point to another, we can only use combinations of A's and C's. Alright, so if I want to go from L to P, then I would go A plus C. I'd go along from L to M, and M to P would be C. So A plus C, or I could go C plus A. It doesn't matter which way round you do these. Okay, and all of these are equal, so M and N, M to N is the same. So if we were to go from O to S, okay, we start at O and we go O to P, that would be an A, and then I go C from P to S. Okay, if I want to go from T to P, alright, I'm starting at T, I have to go minus A because I'm going in the opposite direction of the arrow, and I'm also going minus C. Alright, so I'm going backwards against what the vector should be doing. When I look at A plus C and A plus C, so O to S and that line from O to S and L to P there, then you'll probably notice that these two lines here are parallel to each other. Okay, they're parallel to each other, and that is because they have the same ratio of A's and C's. So A to C in both cases is 1 to 1. Okay, A plus C. If I was to go from L to S, for example, L to S, I'm going A to get from L to M, and then I go 2 lots of C, C plus C. And in this case, the ratio of A's to C's is 1 to 2. So L to S is not a parallel line to the others because the ratios of A's and C's are different. And this is the whole premise around parallel lines, straight lines, all of the proofs by vectors, is understanding that to be parallel and on a straight line, the ratios of the vectors have to be the same. Okay, so let's have a look at a question here. Let's say that X and Y are midpoints of those two lines. Okay, so I'm going to go from X to Y, and I want to show that they're parallel to the other two lines that we did earlier. So going X to Y, I want to show that that's parallel to my others. So to go from X to Y, I need to go from X to N and then add N to Y. So X to N is half the amount of A, so half A, and N to Y is half the distance of C. And I can show that they're in the same ratio by factoring out the half, and I get A plus C. And you can see now that the 1-to-1 ratio has now appeared because I've factored out the half, and I've proven that they're parallel to the other two because they're in the 1-to-1 ratio. If I leave it as half A and half C, that's not really enough. We need to factor out that half. Okay. If I was to say, prove that L to T is a straight line, if I wanted to prove that L to T is a straight line, then all I do is I choose a point that's on the line L to T. In this case, I can kind of split it in half, but sometimes it's like 2/3 of the way or 3/5 or something like that. But I choose a point that's in common, so I can go L to P and P to T. If I can prove that those two lines are parallel to each other and they have the point P in common, that must mean that it's a straight line because I've got two parallel lines. They're not necessarily on a straight line, but once I have a point in common in space, they line up and become a straight line. So I've already done L to P, and that usually happens in the question is you use the stuff that you've already done in part A. But now I just do P to T, and I go A plus C. So because they've got that point P in common, and they're both in a 1-to-1 relationship here, that means that L to T is a straight line. Alright, so they're usually a bit more complicated than this. They have things like you've got a halfway point here, and then this point here, and this point here, and you have to prove that they're on a straight line. Okay? Then you would go from, let's say, A to B, B to C, and then you would factor out the number to show that they're in the same relationship. Okay? So A to B, it might be, I don't know, A minus a half C, like that. And B to C might be half A minus a quarter C, like that. And it's not easy to see that they're in the same ratio, so we factor out a half and we get 2A minus C, like that. We factor out a quarter and we get 2A minus C. And the bracket proves that they're in the same ratio because they've got the ratio of A to C is 2 to 1. Alright? So that's how we do vectors. That will be enough to enable you to answer virtually all of the questions with vectors. If you can show that they have the same ratios, you'll be good to go. Okay, apparently there's some basic probability on the first paper, but there's more likely to be harder probability in the second one. A question like this is a very common one. We've got red counters. We don't know how many green there are, but we know the probability of picking a green and a green without replacement is 3/8. So what we need to do is to draw our probability tree here, and we'll go red and green. So the first one for red would be 6 out of the total, okay, which we don't currently know. And to go green would be, we don't know green or the total. So if we assign a value to the total, let's call it x is the total, then red would now be 6 out of x, okay? So red would be 6 out of x, and green, let's say there were 20 in total, we would work out the green by saying, well, it's 20 minus 6. So we do x minus 6 for greens, because we know that there's no other counters in the bag, and we put that over x. Alright? Now, as we move down the branches, because we're not replacing it, to go green again, we would have 1 fewer green, so we'll take 1 away from the greens, x minus 7, and the total would also have been reduced by 1, x minus 1. Okay? So, you know, if you had green, let's say we had 14 out of 20 for green, and then it would go down to 13 out of 19. So we're doing that kind of thing, but with algebra. And the probability of multiplying these two together gives you 3/8. So we're starting to generate some algebraic equations here. X minus 6 over x multiplied by x minus 7 over x minus 1. Okay? We multiply the top and the bottom together, so we get x minus 6, x minus 7 over x brackets x minus 1 equals 3/8. And then we're going to solve this equation. We're going to cross multiply, so we're going to take the x brackets x minus 1 up here, and we're going to take the 8 up here to clear that fraction. And we get x squared minus 13x plus 42 equals 3x squared minus 3x. 8x squared minus 804, I think, plus 336, is that? I should probably check that. 8 times 13 and 8 times 42. Okay, and we've got minus 3x squared and plus 3x, so that I can get an equation to solve. So 5x squared minus 101x plus 336 equals 0. I'm not going to try and factor that. Let's put it in the quadratic formula, but we would do it on our calculator. Minus 101 and 336. So we get x equals 16 or 21/5. So x equals 16 or 4.2. We can't have 4.2 as a number of counters, so we would ignore that one, and we would say the total is 16. So how many greens? We subtract 6, we'd have 10 greens, like that. Quadratic simultaneous equations. Remember, if you have a quadratic, something like that, and you have a line, then you're getting 2 intersection points compared to your linear equations where you get one set of x and y coordinates. So our job with this is to substitute the linear equation into the quadratic. It's much easier to substitute for x, so we're going to do x equals 7 minus 2y here, and substitute that into the quadratic. So we've got 7 minus 2y squared plus 2y squared equals 27, and we multiply out these double brackets. We're going to get 49 minus 28y plus 4y squared plus another 2y squared, and I'm going to bring 27 over to get a quadratic in 0. So we've got 6y squared minus 28y. 49 minus 27 is 22. And I can divide through by 2 to get 3y squared minus 14y plus 11. So 3y and y, and there's going to be a 1 and 11 in here. So we want 2 minuses and an 11 there and a 1 there. So 3y squared minus 3y, yeah, that will work. So we have 3y minus 11 equals 0, y minus 1 equals 0, so y equals 1, and 3y equals 11, so y equals 11 over 3. We've now found the 2 y coordinates of these, and they're not correct on this graph, but we found the y ones, and we're now going to substitute into x to try to get the x ones. So x equals 7 minus 2y, 7 minus 2, like that, and 7 minus 22 thirds is negative 1 third, I think. 7 minus 22 thirds. Yeah. So our final coordinates that we have are x equals minus a third and y was 11 thirds. And our second intersection point is x equals 5 and y equals 1. Okay? They might ask you to do some midpoint stuff with this or things like that, but you could get to that point by substituting in for the linear term. The next topic I want to talk about is the gradient of a curve and differentiation. So in this topic, sometimes they don't give you the actual equation of this graph, and they ask you to find the tangent at a particular point and work out the gradient. So sometimes you have to eyeball this a little bit. You put your ruler on and you sort of draw your tangent depending on what the x coordinate is, and then you would just draw your triangle. So let's say you did one kind of up here like that. Draw your triangle and work out the gradient of the tangent at that particular x coordinate. So we're worried about the x coordinate with this whole topic. If they do give you the actual function itself, then we differentiate this, because differentiating will give us the theoretical gradient of that tangent, not an eyeballed version. So we write this as dy by dx, and then we do 3 lots of the number in front of the x, so 3 times 1, and we reduce the power by 1. 2 times plus 2 is plus 4, and the x power reduces by 1, so x to the power of 1, and then there's a 1 here and a 1 here, so we do 1 times 1 and reduce the power by 1, so we get x to the 0, which is just 1. Alright, so now that we've found this dy by dx, that tells us that if we put the x coordinate into this new function, that will tell us what the gradient is. Okay, so if this point was, say, minus 2, okay, then we would put minus 2 into this new equation, and that would tell us the actual gradient at that point instead of an estimated version. But what we usually want to know when we do this is the turning points. So the turning point is where the gradient is 0. Okay, so there's 2 turning points because this is a cubic graph and it goes up and then down and up again. A quadratic has 1 turning point. So in this case, we have two turning points, and whether it's a quadratic or just a linear term, we put dy by dx equals 0, because that is when the gradient is 0. So we solve this equation, we get 3x plus 1, x plus 1. So our two x coordinates are x equals -1 and x equals -1/3. So you can see that this one here, this is -1/3, and this one is actually at -1. So this is -1 for our coordinate here. If we wanted to find the y coordinates of this, we would substitute -1/3 or -1 into our original y equals, not the differentiated one, because you'll just get 0 again, into the y equals, and that will tell you the y coordinates of this. Okay? What else can we do from this? Well, the question might ask you, which one's the maximum and which one's the minimum? So here we're coming up and then down again, so that is its maximum, and here is going down and then up, so that's the minimum. To prove that, or to show that, we do the second differential. So we differentiate this again, and we get 6x plus 4. That is the second differential, and this tells you whether it's a maximum or minimum. Okay? So when x equals -1, d2y by dx squared equals 6 lots of -1 plus 4, which is -2. And if you get a negative number when you do the second differential, that is a maximum. If we put x equals -1/3 into here, then d2y by dx squared is equal to 6 times -1/3 plus 4. 6 times -1/3 is -2 plus 4 is +2. So +2 is a positive number, so we get a minimum value. All we have to remember is maximum if it's less than 0, minimum if it's greater than 0. We also use differentiation when we have displacement, velocity, and acceleration. So if they give you a displacement and you differentiate it, you get the velocity, and if you differentiate the velocity, you get the acceleration. Alright, so if they're talking about a particle in motion and they're talking about displacement, then it's almost certainly going to be differentiation. Don't use speed equals distance divided by time, because it won't work. Use differentiation, and you're differentiating, let's say s equals, I'll use the same equation as this, t cubed plus 2t squared plus t plus 5. You would differentiate the displacement, they use s for displacement, and ds by dt, that is the velocity. So that would be the same as this, 3t squared plus 4t plus 1. And it might say what's its velocity at time equals 2. So you would substitute t equals 2 into that. And then you differentiate the velocity to get the acceleration. So you'd get 6t plus 4. And it says, when is the acceleration 0? So you put that equal to 0. Or what's the acceleration when t equals 1? Put that into there as well. Okay, so that's how it all links together. The next topic I want to talk about is algebraic fractions, and with these we have to simplify them, add them together, times them, that sort of thing. So when we're doing algebraic fractions and we simplify them, there's usually a difference of 2 squares in there. So in this case we have 2x plus 3, 2x minus 3. So try and spot the x squared and then a minus and then another square. So the numerator is usually one of these, so that we can use that to help us, but we can also use our calculators to solve this and get our 2 brackets as well. So 2x and 3, if that works, we'd have an x and a 1, and they're both positive, so let's just check that. 2x squared plus 2x plus 3x, yeah, that's 5x. So now we've factored this, we have a bracket that's the same in the numerator and the denominator, so our final answer is x plus 1 over 2x minus 3. So you might be expected to do something like that with one of these fractions. When you have to add algebraic fractions together, then we need a common denominator like we do with normal fractions, like a quarter plus a half. So what do we do usually? If it was a third plus a quarter, we would multiply the 2 denominators, and then we would do 4 lots of 1 and then we would add that to 3 lots of 1, crossing those over. Okay, so we cross these and multiply these. So what we're going to do here is we're going to do on here, we're going to multiply the two denominators together to get x brackets x plus 1, and then we're going to cross these and add them together. So we've got 7 lots of x plus 1 plus 3 lots of x, and that will become 7x plus 3x is 10x plus 7 over x brackets x plus 1. Okay, so when we're adding these, we get this common denominator and cross multiply. Sometimes when we have functions and things, we have something like this, 1 plus 4 over x. Students don't know how to put those together. So if I wanted to turn 1 into a fraction with x on the denominator, I would have to have an x in the numerator so that when they divide, they still give 1. So if you want to turn a number into an algebra term like that, we just multiply top and bottom by x in this case. So when we've got the 4 over x now, we've got that common denominator, so we get x plus 4. Alright? And when you have a single thing on the denominator, sometimes students, if you have like 4x plus 1 over x plus 2, and they think, oh, I can cancel the x's like that, which you can't do. But if you have 4x plus 1 over a single term, like a 2 or the x, then we can actually separate these into 4x plus 1 over x like that, and the x's cancel. So you get 4 plus 1 over x if you're going the opposite direction. Alright, so we're just reversing that process here. So if you want to get that common denominator, then multiply the number top and bottom by x. Final thing I want to talk about is transformation of graphs, and we usually use the trig graphs here. So we've got sine here and cos here and tan. So what I've sort of noticed using a calculator is you can use the table of values to double check your answers with this. Let's just take a little step back and double check where these graphs go through. So that goes through 180 and 360, and its maximum is at 90 and its minimum is at 270. And for cosine, we go 1, negative 1, this goes through 90 here, 270 there, its maximum is at 360 and 0, and its minimum is at 180 there. With tan, it goes through 0, it has asymptotes at 90, 270, this goes through at 180, like that. So if you're not sure about asymptotes, it's sort of approaching that line but never touches it. We've got 360 here. They never seem to ask about tan, so saying that, they probably will this time, so make sure you know what tan looks like. So if you're transforming a graph, there are about 8 ways you can do it. You can go up and down, you can go left and right, you can stretch it or squash it in the y direction, or you can stretch it or squash it in the x direction. Alright, so if we have a graph like f of x equals sine x, like this, then the easiest thing to do with this graph is to add something, like let's say a here. We're going to do f of x plus or minus a outside of the brackets. This would make sine x plus or minus a. Then that's going to shift the graph up and down. So positive a, negative a, like that. Positive a, like plus 2 or something like that, will shift the graph 2 units up, and 2 units down, minus 2, like that. Okay? If I put my b, let's use b here. Let's do b f of x. So something like b sine x. That could be a 2 or a 3. Then that will stretch the graph in the y direction. So 2 sine of x will be like sine x, but it will go double the height of the original graph. Same number of waves. So if b is a number greater than 1, okay, like 1.5, 2, 2.5, 3, then it will stretch it in the y direction. And if it's a fraction, like between 0 and 1, so 0 to be 0, 1, like that. If it's between 0 and 1, it's going to be a squash in the y direction. So if you've got half f of x, it will be a squash in the y direction by a scale factor of 1/2. Then, if we talk about left and right, we're talking about inside the brackets. So let's use C here. Then, if we have f of x plus minus c, and that would look like sine x plus minus c. This is comparing back to our original graph here. Then with x, it's always the opposite way around to what you think it's going to be. So x plus c, you think x is going to go plus in the positive direction, but goes in the negative. So plus would take you to the left, and minus would take you to the right. So sine of x minus 30 would shift it 30 degrees to the right. And I'm going to use d here. If we have f dx, so that would look like sine 2x. You think that would be stretched like that, but it does the opposite of what you think, so it's going to be a squash scale factor 2. So if it's bringing it sort of inwards like that towards the y-axis, that's when d is between 0 and 1, 0 to 1. And if it's greater than 1, then it's going to be stretched away from the y-axis. Okay, so sine 2 of x is squashed towards the y-axis, and sine half of x is stretched away. Alright, we also have minus f of x, which is a reflection in the x-axis, and f of minus x is a reflection in the y-axis. Alright, so in minus f of x, if you have like a 0, 4, then the y coordinate becomes its minus, so 0, minus 4. So you can see that everything's going to go upside down, and if you do it on the minus x inside the brackets, it's flipped this way around. Alright, now I've written calculator here because I wanted to show you on the calculator the last thing I'm going to talk about. You'll be pleased to know, table of values. You can actually do sine x on this and go from 0 to 360 and go up in steps of say 30 degrees. So when you get this, you can see, I'll try and make this a bit bigger. 0, 0, 30 degrees is 0.5, 90 degrees is 1. So when you look back at your sine graph up here, you can see 0 to 90, it's increasing from 0 to 1 on the f of x, that's the y value. Alright? Now if they say to you, right, we've transformed the graph, and we want you to tell us if it's like a 2 or a half or 30 and things like that, and you're not sure, then you could go back to this and say, right, I think it's a 2, like that. And you can see that the y values have been stretched, and you could actually kind of put that onto the graph and see if it's the same as what you have in the question. Okay, so let's give you an example of, let's say it's got a graph and it goes sort of down like this, and it goes up to 2 and minus 2. All right, and it's telling you like it's a cos x, and you're like, is that a 2 or what, is it a minus 2? I'm not too sure. You can put that function into your calculator. So let's do cos of x, and I'm going to put a 2 in the front because I think it's doubled in its stretch in the y direction. And you get your values, and you look at the graph and see 0, 2, yeah, that's right. 90, 0, that's looking about right. If it's got in here like an x plus b, like that, x plus b, so that's telling you it's been shifted, well, you can go into your graph, your calculator, and say, oh, I think it's gone 30 degrees to the right, but I put plus 30 by accident, because 30 degrees to the right should be a minus 30. And you do this, and you get your values, and you go, hang on a minute, that's not quite right, it should be the other way round. So you go back into here and you do x minus 30, and you get your values, and you go, yeah, that's exactly the graph that I've got in front of me. Or what's happened in the last couple of years is that they actually put a minus in here, minus 2 cos, and it flips it upside down, and students didn't get onto that. So you can use your graph to predict the table of values and get your answers for you. Okay everyone, I hope that's been useful to you. The topics that are coming up I'm not 100% sure about because I haven't seen the paper. This is based on information that I've been given in the comments for my other videos. So I've tried to create as much content as possible for your 2H paper on January the 15th. So if you have any questions, email me, mrwakeling@bowtieteacher.com, or comment below and I'll try my best to support you. Otherwise, have a fantastic exam and I hope that you get the grades that you're looking for. Good luck.